So today we have Dr. Stein, as Dr. Stein mentioned, and I just wanted to say a few words. I've worked with him for several years now, and so Dr. Stein is a senior scientist at Sandia National Labs, which is located in Albuquerque, New Mexico, and he's also the director of the PAC Center. And the PAC Center is basically a photovoltaic accelerator to commercialize new technology. He's also the founder of the Photovoltaic Performance Modeling Collaborative, and he represents the United States in the International Energy Agency on Photovoltaic Performance and Reliability. So the International Energy Agency is an organization that's international and that provides analysis, data, and policy recommendations on energy. Dr. Stein is a leader in photovoltaic performance and reliability research, specializing in the modeling and analysis of new technologies. Dr. Stein received his doctorate degree in Earth Sciences from the University of California, Santa Cruz in 2000. And right after that, in 2001, he joined Sandia. Now, today's talk, Dr. Stein will provide a high-level introduction to perovskite photovoltaics, and he will explain why there is so much excitement surrounding this new technology. And he will also touch on the many challenges facing its commercialization. Dr. Stein will also present information about Sandia's extensive student internship program. So whether you have the minds of an entrepreneur or you're looking for an exciting internship opportunity, you have a lot of good information coming your way today. So without further delays, let's welcome Dr. Stein. And Dr. Stein, you have our undivided attention.
Thank you very much, Hubert, for the kind introduction. And I'm happy to speak on a topic that I'm quite passionate about, and I hope I can explain it. Please, if you have questions, I guess we'll have a chance at the end, and I'd be happy to answer questions, and I can stay longer if needed. So I'm going to talk today about an exciting new technology called Perovskite photovoltaics. I'll probably call it Perovskite PV for short, but it is a technology that was invented in 2009 as a completely different type of solar cell than what we usually have, which is crystalline silicon. And I'll sort of talk a little bit about the differences between each of these. So I want to start out with a brief history on sort of the photovoltaics or PV cell and modules. Modules are basically the solar panels. It has basically a 50-year history with the conventional technology, which is crystalline silicon. And as I said, in 2009, 16 years ago, we had an invention in Japan of a new type of solar cell called perovskite, and it's been, ever since then, it's been quite a exciting development, but there's still a lot of hurdles in terms of commercializing, and that's kind of what I wanted to talk about today. And I'll kind of give a brief overview on the differences of these different technologies and some of the hurdles for commercializing. And what I mean by commercializing is taking it from the lab out into a large-scale manufacturing and being able to sell it as sort of competitor to what the modules that we buy today. This is a picture from our lab with Dr. Angelique Montgomery, who was my postdoc for 3 years. She's now at the U.S. Department of Energy at the Solar Energy Technologies Office as an intern, like a postdoc intern there. So let's see. So just a quick overview of the PV cell technology. I mean, we sometimes think about the first solar modules from and the first solar cell from 1954, which was Bell Labs when they announced the first practical silicon solar cell. But you have to go much further back, all the way back to Becquerel in France, for the first photovoltaic cell. And the idea here is a photovoltaic cell is something where if you shine light on it, you can generate an electric current from the light. And so he invented something which was basically an electrode in a liquid solution. So it's not really practical at a large scale. You'll also hear, if in a physics class, you might hear about Albert Einstein. He actually won his Nobel Prize in 1921 based on something called the photoelectric effect. And that work was done in 1905. So that kind of is the theoretical basis for how a solar cell would work. And it wasn't until really in 1954 at Bell Labs where they announced really the practical solar cell it was made of solid, not liquid, and it could be hooked up in a circuit practically. And it was only 6% efficient at producing electricity. And then if you move forward, really the first full-size commercial product using a PV cells and putting them into modules was in 1963 at Sharp Corporation in Japan. And I just included these pictures down here. It was a buoy that had 242 watts of PV attached to the buoy, and this is what the modules look like. And you can see they're made up of half circular cells. And I'll get into a little bit about sort of how this technology is made. And if we move forward, 1974, the first building heated and powered by solar and wind was actually in New Mexico. In 1977, the world PV cell production was only 500 kilowatts of capacity. That's 500 kilowatts per year. By 1983, it had gone up to 21 megawatts, which is orders of magnitude larger. By 85, we had cells that were as much as 20% efficient. And by 1999, world production reached 1,000 megawatts or a gigawatt of production. Like I said, in 2009, perovskite solar cells were invented at 3.8% efficiency. By 2024, the record solar cell efficiency for perovskites was up to 26.7%. So I'll show some of this graphically. These are plots that you can get from the National Renewable Energy Laboratory, or NREL. And if you follow the different, these are crystalline silicon cells in blue, different technologies. But if we look at the single crystal non-concentrator, which is the blue solid box, all the way starts with mobile solar in the 1970s at around a little bit over 12%. If we go all the way up to present day, the world record was set for just single crystalline was set at about 27.3%. And then there's another crystalline silicon cell type called heterojunction or a heterostructure, which has gotten up to 27.6. This is essentially in 50 years of silicon solar cell development, it went from about 13% module efficiency or cell efficiency all the way up to 27.6%. So that's great, and this technology forms the basis of like pretty much most of the solar cells or solar modules you'll see out on people's rooftops or in solar plants. So now if we switch to perovskites, you need to focus on the red, the red circles with the yellow in here, and you can see that it started, the record cells, this horizontal line here was when the technology was invented in the laboratory. And the red circles with yellow dots are the perovskite solar cell records efficiencies. And you can see that for single junction devices, those are the circles, that by 2024, we reached 26.7%. And the diamonds are tandem structures. So perovskite, a perovskite solar cell on top of another type of solar cell, which could be perovskite as well, or crystalline silicon, and it's reaching 30.1%. And so you can see that the slope of this line compared to the slope of this line is much steeper. And this is part of the reason why there's a lot of excitement, is because in much less amount of time, the efficiency has risen to almost, basically to compete with crystalline silicon solar cells. So that's interesting, but why would we care? Why do we need something other than crystalline silicon? Or why are people interested in that? So I kind of contrasted these two technologies and why there is so much excitement about the perovskites. Some of the problems with crystalline silicon is that it requires very high temperatures to process the material. This is a picture of some crystalline silicon before it gets melted. And so you have the polysilicon, it gets melted, and then they pull these giant, they're called boules. They're big cylinders of single crystals of this material out from basically the melted material. And that's a very expensive process. It actually is not done very much in the US. It's mostly done in China. And then those boules are then sliced into wafers, which are these picture here. And then there's some processing that's done on these very, very thin wafers to make them into solar cells. And then those are produced into solar modules. This material requires very high purity silicon. So it's a very high tech process that requires big factories with lots of quality control. We typically talk about these in sort of the number of N's, which is the number of nines after the 99.999. So this is like, you have to count the nines here, and that's sort of 7N, and you can go all the way to 10N. So 99.9999999 all the way out. And that just is a very expensive process to get that level of purity. It has very high capital expense, and then this whole process can cost a lot of money, especially at the factory level. So in contrast, metal halide perovskite solar cells are made using very abundant materials, lead, halides, which include iodine, bromine, chlorine. They're very abundant. They use electrodes that are either copper or even carbon electrodes like graphite, and it's a very low temperature process. It's less than 150 degrees C most of the time, which is just a little bit above boiling temperature. And it's solution processing, which is, you can understand that as sort of the same kinds of processes that you'd use for printing a newspaper or screen printing onto a t-shirt. It's a very similar kind of process. And so it could be done on a roll-to-roll kind of factory where essentially you just add layers at different steps in the process, and your module literally rolls through the whole factory and comes out the other end. So there's a lot of excitement in the sense that you can do this whole process in one factory versus for the silicon, you need to produce the polysilicon material, mine it, and produce it. Then you have another factory that makes the ingots and the wafers. Then you typically have another factory that makes the solar cells, and then another factory that makes the modules. So you can see it's a lot more capital intensive. So if we think about the differences between these two, you'd think like, well, the efficiency has reached pretty much the same level, and it's a lot cheaper, likely, to produce it, because it's a single factory, and it's a low temperature process, and it's abundant materials. So why wouldn't we just switch to metal halide perovskites? And so this is this is basically this next step. I'm going to talk a little bit about what are the competing issues that make actually bringing a new technology into a market difficult, and with some specific experiences around solar. Um, and so the first thing is cost, right? I mean, if you can bring something in that performs equivalently and is lower cost, it seems like that is something that might work. And so one way of thinking about costs when we talk about solar modules is a concept that comes out of industrial engineering called learning curves. And so what a learning curve basically it describes is how economies of scale work. So if you're building very small amount of something and you have to build a factory to do it, you likely don't have a lot of experience. You haven't really optimized the process. There's still a lot of costs with the supply chain. It's not optimal. So you get very high prices. And this is a plot that basically shows the price per watt of solar PV modules, and it's on a logarithmic scale, versus the cumulative installed capacity, which is how much of solar modules are actually installed out in the world. And so you can see as you fall along this chart, and these are both on a log-log chart, you get like a linear relationship. And that's actually pretty common with things that have started small and gotten really big, is that with learning and the economies of scale, costs come down. And so this linear pattern is kind of an interesting pattern, but it also means that the more experience and the more we produce the conventional technology, the cheaper it gets. So if you have a new technology, you can't just be cheaper today. You have to be almost like cheaper than it will be 10 years from now in order to have a chance of competing with it. There's some interesting, this deviation here started around 2002, where the prices kind of, it didn't get less expensive even with more. This was a period where the polysilicon material, there was a shortage. And what happened is that China during this period responded by building huge capacity to essentially have more polysilicon, and that then brought down the prices. So some of the recent techno-economic studies have suggested that perovskite silicon tandems could be made for about 35 cents a watt in the US. But if you look at in 2019, we're almost at that with crystalline silicon. And so that's a challenge for perovskites, is that crystalline silicon modules keep getting cheaper. And I think that some of these estimates are not low enough to actually be cheaper than even this very expensive way of making these materials, but largely because they're made mostly in China, where the cost of manufacturing is a lot lower. Another problem you have to work on is what I've shown are efficiencies at the cell level. And this is a paper, this is from a paper that we published a couple of years ago. This was a review of the literature showing where there had been, the blue circles are showing the efficiency of the single cells, and then the red squares below each blue circle were the efficiency of a module made of several cells in series. And you can see that the module efficiency is always lower than the cell efficiency. These green bars kind of tell you by how much. And then they're sorted in terms of area of the module. So this would be, most of these are very small, but there are some larger modules that are over 300 square centimeters, still quite small. And you can see that you basically lose as much as about 10% of the efficiency by going from the cell to the module. This is like an upscaling reduction in efficiency. This is quite a bit larger than you would see with conventional technologies. which are usually, maybe 1 or 2%. And that's basically because the crystal and silicon cells are the only reason why you would lose efficiency is because of the space between the cells in a module. Whereas for perovskites, there's actually, and I don't need to go into too much, but there's dead space because they have to scribe these films to make individual cells. And there's also much higher electrical resistance in the materials that are used. So that's another reason why when you make things bigger, you get more resistance and you lose a lot of current. But there is some hope with making these perovskite modules bigger. This is a picture from a Chinese manufacturer who has made these are perovskite photovoltaic modules. This is kind of what they look like at large scale. You can see on the top, the white picture is sort of where those scribe lines would be that separate the cells. So each one of these strips is a single cell, and then they're connected into series. These modules are about 12% efficient. They have a rating of around 95 watts, and this is compared to about 500 watts for some of the larger crystal and silicon modules that are, upwards of over 20% efficient. So the other question in terms of scaling up these modules, I mean, the cells are efficient at very small scale, but when you bring them into modules and stuff, we haven't seen that the efficiency is rising enough to compete with crystal and silicon. So one of the programs I work with is called the PACT program, and we have been we've basically been testing a whole bunch of perovskite modules, many of them quite small, and we've been comparing how long they can last outdoors, which is on the y-axis of this right plot. So this is years either to reach 80% of their initial outdoor efficiency. So it's how long it takes until the efficiency is 80% of what it was initially versus the initial outdoor efficiency. And there's sort of two different ways of looking at this data. The right-hand plot, you can see that this is just showing that we have lots of variability in the initial efficiency. It goes all the way from 1% maybe to over 20%. The symbols with arrows on them are ones that have yet to reach 80% of their efficiency. So if we look at this next month, this is from early January. If we look at this next month, these modules should move up in this plot. And so you can see that there's a good trend that it looks like we're getting modules that are lasting longer, that are more efficient. The same data over here is just plotted slightly differently. It's initial daily efficiency on the y-axis from when we actually installed the modules. And these are modules we're getting from startup companies in the US mainly. And you can see that the early modules didn't last very long because they have very short tails on there. But the ones in blue here are still on test at our site. And so you can see there's a little bit of a correlation as you move to more recent times, modules are lasting longer. And the size of the circles also show you that some of the modules are actually getting bigger. So these larger circles that are showing up here and over here are modules that are quite, less than a meter squared, but they're more than 100 centimeters squared. Another thing that's important for commercializing PV panels or solar panels is really they are considered by developers to be almost considered as commodities. And what I mean by commodities are things that are interchangeable. So one good example of a commodity would be eggs. When you go to the grocery store and you buy eggs, you have many different brands to choose from. but typically we don't really care that much about what brand we get. We might like to get organic eggs or not, or large or small, but um, it's it's a commodity because we can easily switch between different brands. And for developers, PV modules, especially crystal and silicon ones, are considered to be commodities. Um, and part of that is that they have to be very, very comparable. And so the expectation is that consistency between different modules is very high, like plus or minus 1 to 2%. So if you buy 10 modules and you test them, they're going to be very similar. This is just an example of some perovskite modules very early. This was a couple of years ago, but this is looking at different ways like efficiency, power rating, fill factor, current and voltage ratings. And the 0.5 and 1, this would be plus 100% different from the mean, and minus 100% different. You can see that all this batch of essentially similar modules is it varies quite widely in terms of their performance, and that's going to be a problem for commercialization. So we need more consistency. The other thing is testability. If you're making modules at a module factory, typically the conventional modules, they're test on a pulse simulator. This is a picture of one of our pulsed simulators at Sandia. It's essentially a giant box here that you lay a module face down on, and it flashes a light very quickly that's highly calibrated, so it's always the same brightness. And then we measure the electrical current and voltage coming off of the module through the wires here. And this is also a process that's done while the modules are being manufactured in a factory. And it takes literally a second to make a measurement. And this could be on a conveyor belt, for instance. And then they use those measurements to bin the modules or separate them out into different power classes. So you can buy 200 watt modules or 205 watt modules or 210 watt modules. But as they're being made, they may come in at, they may measure at 206 watts, and then they'll be sold as a 205 watt module class. If you're making perovskites, there's a problem because this material doesn't actually, you can't measure it on a flash simulator. The way you have to measure it is actually using a continuous solar simulator, which has lights that basically you have to put the module on the simulator, and it can take several minutes for it to stabilize for each test. And the implication of this is that it will slow down manufacturing. And that is, if you slow down the process, that costs more money. It adds more money to the whole manufacturing process. Another issue with perovskite modules, like I said, most of them are made, they're metal halides, and the metal is usually lead. And so they have, one of the main ingredients is lead iodide. Lead is highly toxic. It's highly regulated. And, what we've learned about lead is that there are no safe exposure levels. So many toxic materials, if at very low levels, may not be safe. Lead is an exception, and that over time, that regulators have basically, there's no safe level, so you really need to eliminate it from the environment, and that's part of the reason why it was removed from gasoline and from paint and stuff. And so this just is a cartoon that kind of shows that throughout the life cycle of the module, from manufacturing, you can think of fires, like what we've heard about in California. If you have solar plants that are burning with lead in the smoke, that could be a hazard for workers and for firefighters and for residents. Severe weather could break modules, and rain could have the lead leach out. So there's a lot of risks all the way from like manufacturing to getting rid of the modules at the end of their life. It causes some problems that are less of an issue with crystal and silicon modules for a number of reasons. So what are we doing? We are so Sandia National Labs is a FFRDC. It's a federally funded research and development um, corporation that works basically with the U.S. government, and in our case, the Department of Energy. And so we we work sort of collaboratively with the Department of Energy to try to help companies that are trying to commercialize work through some of the problems that I just discovered or just discussed. And this is just a list of some of the published matrix of performance targets that the DOE has put out for perovskites. And these were put out like 3 or 4 years ago. So, we're looking at PCE is the efficiency. It's the photovoltaic cell efficiency. So for single junction devices, 18%. And if you remember back to my plot, if I go back here, 18% is like around here. We don't have very many modules that are actually above 18%. We have a few, but they're very small. We're looking at, and then if you're with tandems or perovskite only tandems, we have much higher targets. We're looking at getting modules that are at least 500 centimeters squared with at least 4 cells. We have a few that are bigger than 500 square centimeters, but not many. Most are 100 centimeters squares or below. And then there's a bunch of other kind of goals here. I mean, one important one is actually getting more than a kilowatt or at least 20 modules for outdoor testing. And currently we're really only able to get 2 or 3 or 4 modules for outdoor testing, which are much, much lower than 1 kilowatt. So when we get these modules in, we put them outside, and this is actually a joint program between Sandia and NREL, which is the National Renewable Energy Laboratory. And this is some pictures of some of these devices on some of our trackers. These are pictures of perovskite solar cells and modules at NREL. We do characterization indoors. We started this program in 2021. We've received over about 600 single junction and tandem mini modules for testing. We do indoor testing and outdoor testing. And this is just sort of one example of a project that we have at Sandia. We actually have a whole bunch of other projects related to solar energy. And so I hope you learned something about this. I do want to kind of switch over to talking about internship possibilities, because we're always looking for motivated interns at both of our labs, and I'll actually kind of introduce the national laboratory system as a whole, because if you're interested in science and engineering, these are great resources, and they're located all around the country, and every single one of these labs have internship programs. I can speak for the program at Sandia. Sandia is one of the largest, actually I think it's the largest laboratory in this whole complex, and we have over 16,000 employees at our, at 2 different sites. We have a site in California as well, and we bring in hundreds of interns every summer, and also have year-round interns. And I know that NREL has a vibrant renewable energy internship program up in Colorado. Livermore Lab in California. There are all sorts. There's Brookhaven in New York, the NETL, the National Energy Technology Laboratory. There's Savannah River and Oak Ridge National Laboratory, which have like a whole bunch of basic science and also nuclear engineering types of internships. So I've included the sort of, if you're interested in Sandia and energy-related programs, you can search for Sandia and then FORCEE, F-O-R-C-E-E, which is a energy-specific internship program. NREL has a STAR program, or student in training, and these slides I think will be available. But a lot of this stuff you can find by just looking up the national labs, going to the lab that you're interested in, or just, each of these labs' websites, and looking at their HR sites or their career sites, and there are many, many thousands of internships listed. And I mean, it goes all throughout, like biology, energy science, renewable energy, electrical engineering, all sorts of different, computer science. There's lots of computer science work. So I'd encourage you, if you're interested. They pay very well. The internships are all paid and are quite competitive. And I think the other thing that's important is don't just rely on. I guess I'd recommend not just relying on just applying for positions, but go beyond a little bit. Ask your professors, ask friends that have done internships at the same school that you're at. Go to your career centers and try to find where people have had success. Also, be willing to try and learn new things, because a lot of times you might think you want to do something. I mean, this was true for me. I was a hydrogeologist, and I worked for a while at hydrogeology, and then I changed careers sort of mid-career, and started learning about photovoltaics. So I think it's good to kind of be willing to kind of come in and help out a research program where they're, with their goals that they have, and be excited about that. And then also just focus on your resume, on your skills. It's less about what you have done and more about what you have learned to do. And so, like, for example, like if you have experience using a piece of software, that's a skill, because otherwise it takes training. Or if you have experience coding, or if you've worked in a laboratory, listing the machines that you've learned how to use, all of those things are really good. So skills, accomplishments, if you've completed a class with project that involved like completing a project, like it's really useful to express that in a way that is like, what was the aim of the project, and what did you accomplish those aims? And it's also good to just include your interests, I think, as well. So that's all I have. I hope I haven't gone too much over time, and I'd be happy to have questions.
Oh, thank you very much. Very great talk.